Did here started the lecture before pressing record. So this, I was just kind of saying that these properties of logs, which aren't going to be a massive deal, if you need them, they're here. How do I remember them? Well, the way I remember them is I actually think of log as kind of a transform. So basically you got this place over here with positive real numbers, and you can multiply them together, and you have inverses. You can multiply by 1, it's the same thing. And over here you've got all the real numbers, positive and negative, and you add there, add and subtract. And multiplying by 1 is like adding 0. Both of them do nothing. And so you kind of have this analogy between multiplication and addition, division and subtraction, powers and multiplication, that are just manifested. It's just a way of thinking about these laws where multiplication gets turned into addition, division into subtraction, powers into multiplication. That's all I was really saying. And these things are all here. Page 165. Now we're going to do some examples. It's just more work with logs, because they're hard to understand. Like, you probably need to, it's probably a thing where normally I say, oh, watch the lecture and do exercise. You might have to see a good few things to maybe finally make it click. So here, this is just equal to x, because log base, and actually I never said this, but this fact that a to the power and log base a are inverses is here. Okay. So if you do a to the power and then log base a, the log base a gets rid of the a to the power, you just have x. Similarly, a to the power gets rid of log base a, you just have x. So these are the inverse properties. Okay. So log base 3 and 3 to the power are an inverse pair. One undoes the other one. Alternatively, we can kind of explain this with an arrow diagram. So, okay, be careful here. So the first blob would be the real numbers. Second blob is positive real numbers. And we're starting with x. And we do 3 to the power. Get 3 to the power of x. And so that is the 3 to the power function. And of course, log base 3 is its inverse, so it'll bring you back to x. So log base 3 of 3 to the x is equal to x. Okay, done. Excuse me. Similar story here. 4 to the power and log base 4 are an inverse pair. So if you start with 42 and you do log base 4, 4 to the power gets rid of it. So this is just equal to 42. Again, we can draw it with an arrow diagram. This time the first blob is the positive reals. Second blob is all the real numbers including negative. So starting with 42, and you can do send that to log base 4 of 42. That's a function. Log base 4, and then the inverse of log base 4 is 4 to the power, and that will bring you back to where you started, 42. Log base b of 1. So if you want, you can think of this as probably too difficult, but 1 is to multiplication as 0 is to addition. But I'd say probably the best thing to do here is there's probably two options. We'll look at both of them. The first one is let this equal to x, and then do base to the power equal to the number, and then ask yourself b to the power of what gives you 1, and you have to kind of remember stuff from previous x equal to 0. Or alternatively, you could write 1 as a power of b. These are both kind of tricky, but 1 is b to the 0. And log base b is the inverse of b to the power, so this should be just equals 0. Okay, this one, now this is where it's getting a bit harder and the calculator isn't there for you. We'll do two ways. So the first way is you let it equal to x, and you base to the power is equal to the number, and now you have to be able to write the square root as a power. And I'm recommending that you write in that square root is the power of a half. So square root of b is b to the half. And now either using the theorem that said that when you have two like powers equal, the powers themselves have to be equal, or else you could actually use log base b here. Both sides to get rid of both of the b to the powers, so x is equal to half. And when I write this x, it's equal to this. And when I write this x, it's equal to this. Alternatively, log base b of root b, you say, I want to use, it's essentially this thing, that log base b and b to the power of inverses. So if I could write square root of b as a power of b, you would just have to know that the square root of b is b to the power of a half. And then they're inverses of each other. Excuse me, so that's to be half. There's one thing that I probably should put up the top. Log base b of b. Well, what's that equal to? Well, b is b to the power of 1. And b to the power, log base b are inverses, so this will give us 1. Okay, and this might actually, yeah, okay. Another one, solve this little equation. Okay, so again, you work like the onion, work from the outside. The first thing I want to get rid of is this log base 2. Now at this stage you want to be starting to kind of feel what is, that log base 2 is just the inverse of 2 to the power. So if I do 2 to the power of both sides, it'll get rid of this log base 2. So 2 to the power will get rid of the log base 2, so I have x squared equal to 2 to the power of 3, which is just equal to 8. And now here, now there's a subtlety here that I don't know will we push in an assessment situation. We'll see. The thing is, when you've got x squared is not 1 to 1. So like if we draw the graph of x squared, so say if this is y equal to b, there are two numbers that square to give you b, plus the square root of b and minus the square root of b. So we have to be careful when we've got x squared equal to, so x squared is like the y here, so a y coordinate equal to something, there's two solutions. So what I usually do is I'll say just beware there's two solutions and then work away and just remember there's two solutions. But we haven't done much on quadratics really in this, so have to be careful. So we're noting there's two solutions and we're saying that the inverse of squaring is square root, and we're going to do the square root of both sides. We're going to say it gets rid of the square. I think we spoke about this is just 8 back previously, but we have to note that it's not 1 to 1, so it's not a perfect inverse. There's actually two things that could have came from, plus or minus 8. If you want to do some kind of decimal rounding, you can, but I would like 4 significant figures. So 4 significant figures would be 1, 2, 3, 4. Do you have to round the last thing? No, 2.828. Okay. Now this thing, so what is the thing we're trying to get rid of here? It's the 4 to the power. That's the outside of the onion. What is the inverse of 4 to the power? This you should start to think 4 to the power, log base 4. Apply that function to both sides and you get x is equal to log base 4 of 100. And this really only goes, as far as I'm concerned, this is the answer. But you can, if you want, go into the calculator, log base 4 of 100, 4 significant figures anyway, 3.32, and because it's 19, I'll round that to 2. Okay, so that's just knowing that the inverse of 4 to the power is log base 4. Okay. And this one, now this one's a bit nasty, right? So here, you'd like to get rid of the 4 to the power. This is where I said one of them was going to come in, possibly this one. So the 4 to the power is nasty, the 3 to the power is nasty. I can't get rid of both of them at the same time. What I could do, and I'll just write it down here, is because log base b of x to the n is so that to the power of n, a log will turn that into multiplied by n. If you identify the fact that the x's are in powers, and you would like to get the power. So that's a difficulty. You're not going to get rid of something. It's a difficulty. You could take a log, any log. Now it has to be the same log on both sides. You can't do log base 4 and log base 3 because they're different functions. The inputs be the same, the outputs be different. You could say, oh, I'll use logs because logs will get this power out of there, and then things are easier. That's certainly the way you could go, and you could do whatever log you want. So as a computer scientist, typically your default log would be log base 2. So you could do log base 2 of both sides. Now what I'm going to suggest instead, and maybe if I have time, well, I will have time. If I've space, I'll do log base 2 down here. But what I would say is, rather than doing that, could we just make it a little bit easier by maybe just getting rid of the 4 to the power? And what is the inverse of 4 to the power? Log base 4. So let's get rid of the the 4 to the power. So do log base 4 of both sides. It'll get rid of the 4 to the power here. So you've got 1 minus 2x is equal to log base 4 of 3 to the power of 4x plus 1. Now that's pretty good. We have made things easier. Now we still have to use this. We have to understand that the logs turn the power, instead of the power of 4x plus 1, into multiplied by 4x plus 1. So we're not doing anything. We're just using this identity. You see these brackets? Now these are hard questions, so this will test some of us greatly. Now here you've got another choice, right? And it boils down to, are you comfortable or not that this is actually a number? If you're comfortable, it's a number, and it's what I'm going to deal with. You'll work with it. Otherwise, what you'll do is you'll round this at this stage to maybe 4 significant figures. Now your answer is going to be slightly off. We won't mark you down for this. But if you're a bit stuck here, this is what you do. So it's 0.7925. I recommend 4 significant figures. 7924, but the 4 rounds up because it's an 8. So if you're a bit uncomfortable here, now all this could be quite difficult, and that's absolutely fine. You're kind of pushing yourself here. I'll be wanting you to focus a lot on functions, because I suppose the thing is, the better you work on functions, the basics you'll be better at, but the little bits of algebra you might still be struggling. But anyway, so you could put in this number here. Now where are you? Look at the difficulty. Well, on the right hand side, I've got a bracket. If I multiplied it out, that would help, wouldn't it? So I'm going to use this as a number as it is. You can use this number if you like. So 4x by log base 4 of 3. That's 4 by x by this number. I'm going to do it in a different order. I'm going to do 4 by this number. Sorry, I have a tickle in my throat now. Excuse me. Plus 1 by this. I'm okay. Right. Now what's the difficulty? The difficulty now is I'm trying to solve for x. I've got x's on both sides. Now what I want to do is I want to get all the x's on one side. So now I'm going, there's no difference between the sides. Like they're left, right, whatever. Like if a is equal to b, b is equal to a, you can swap them around if you want. I'm going to go get all the x's on this side because it's plus over here. Okay, so I want to get this out of here because this isn't a multiple of x. And I want to get this out of here because I want the x's all to be on this side. So I need to do something to get rid of both of those. And I'm going to be a bit fancy here, and I'm going to write a composition. So I'm going to, well, how am I going to do it? So, okay, I'm just going to write, I'm going to add 2x to get rid of this. And I'm going to add minus log base 4 of 3 to get rid of this number. So I'll add this to both sides, so the plus 2x will get rid of that, and I'll have 1 plus log base 4 of 3. You can see why some people might prefer to put in the decimal number, and that's okay. Equal to, over here, so I've still got 4 log base 4 of 3 times x. I've got the plus log base 4 of 3, I'm taking that away, so it's gone, but I'm adding 2x. Okay, and now what I'm going to do is I'm going to swap them around. Now I'm not moving anything. If that's equal to that, that's equal to that. And I'm going to take out on the right hand side the common factor of x. So if I take out the common factor of x on the right hand side and now right on the left, I have x times 4 log base 4 of 3 plus 2 equal to 1 plus log base 4 of 3. And then my final thing is to get x on its own, it's multiplied by this number. And this is the weird thing, which is like it's kind of, it seems obvious, but if you, like this is a number. And I say, what? Well, log is a number, and you multiply a number by another number, you get another number. And when you add a number, you get another number. So this is all one number. And if it's a number, I can divide by it. So I'm going to divide both sides by this number here, 4 log base 4 of 3 plus 2, to get a final answer of x is equal to 1 plus log base 4 of 3 over 4 log base 4 of 3 plus 2. And if I want, I can estimate this to maybe 4 significant figures. 1 plus log base 4 of 3, 4 times log base 4 of 3 plus 2. 4 significant figures, 0.3467. It's an interesting exercise. So there's no rounding here until the very end. If you use this rounded figure, how far off are you? It's something to check out. There's no doubt that this is a difficult question. It is. One thing I forgot to say, and I should have said it previously, and it's hopefully it's something I can remember to put in the things, is that with the equations you can check your answer. Now there's one issue where if there's multiple solutions, and I actually just lost one here. So you can kind of check your answer, but you might have forgotten an answer. So you can check your answer here. So for example, log base 2 of x squared. So now if you use this one, which isn't ideal really, do I get about 3? Yeah, you're getting rounding here. Now I will tell you, if you just plug in numbers here, you are getting 0 marks. That's just not mathematics. Now you might say, oh, but I got the answer. And you might have noticed we haven't been too fussy about how you do things. In general, if you get the answer, it's okay. But it's not that the method has to be okay. It's just the answer, just writing down the answer, like by messing around, by plugging in values of x. How do you know there's not multiple solutions? So just writing down one answer, you haven't got certainty that there aren't other ones. So it's not good enough just mess around with values. You will get no marks for that, 0 marks. Unless you could actually argue that you know there's only one solution. And you actually could do it. So for example, with this one, it'd be a bit bonkers, and I really wouldn't like to give you the marks, but if you were able to say, oh, 4 to the x is an increasing function, and therefore it only has one solution, and then you go messing around on a calculator. If you showed me that much insight, I'd probably give you the marks, but if you can do this, you can probably do this. Because if you can understand the one-to-one aspect of a function, you probably understand inverses as well. But in terms of an assessment, you can certainly check your answer, and if your answer doesn't work, as it were, you can try the question again, maybe after doing other questions. So it's just exam technique more than anything. So I'll try it here. 4 to the power of 1 minus twice 0.3467. Let's call it 1.5, and the other one, what the hell is going on here? Ooh. So this is exactly why we do this. Okay, I'm wondering so I'm getting 13 here. Yeah, so this is why we do this. You check your answer. I've made a mistake. It's embarrassing now, but I have to go through it and find it. So 4x times this, 1 times this, okay. 1 plus log base 4 of 3. Yeah, to get the common factor of x, yeah. 1 plus log base 4 of 3, 1 plus. Now, did I make that now the mistake in the calculator course isn't so important because I've got the right answer here. So this is why you would do that. I actually didn't do that on purpose. I'm not in the habit of making a fool of myself on purpose. Oh dear. Okay, let's go again. This one here. This is a mess. Like I can see that this, oh God. This is a small number, but this is a big number. What is going on here? Where has it gone wrong? There's something interesting here. There is something interesting. Oh, you dumbass. This is minus, this is negative, sorry. So this is negative, and that makes this number different. So here you see the value of checking your answer. And if you saw that earlier, well done. You must have been screaming at the screen. So it's approximately 0.04. That's the first significant figure, 0.14. And now I can check my answer. 4 to the power of 1 minus twice 0.04014. It's coming out 3.57. 3.57. 3.57. So that's how you can do a little check. Right, so that was a great lesson for everything. There's some notes here. So there's certain bases that are more important. It's base E, base 2. If you want to read why base 2 is the most important in computer science, have a read for yourself. The importance of base E is basically so you have 1 to the power of x, this is 2 to the power of x, and this is probably, this is 10 to the power of x. Doesn't look like it, but let's just say it is 10 to the power of x. See the way the slope, as the x gets bigger, the y gets, so as x gets big, the y gets big, and the slope, now we won't define what the slope is, gets big. So this one here is e to the x. So see this one, it gets big and the slope gets really, really big. This one gets big, but the slope doesn't grow so fast. And this one is kind of more in the middle. Well, e to the x is the one where the slope at every point is equal to the y value. It grows at the same rate. Okay. The ln stands for log natural. Okay. Further remark, there's stuff there about base 10, which used to be very important, but isn't really important in my opinion anymore. So that's, if you're interested, there's some reading to do there. Okay, I think we will pause and then we'll have, we'll do some little theory here for logarithmic equations. So the exponential equations will be of the form kind of a to the power of some formula in x equal to b to the power of some formula of x. You can do whatever log you want on both sides. I actually like just getting rid of this a to the power by doing log base a. So that'll get rid of a to the power, and you'll have f of x equal to log base a of b to the g of x. And then you can use a property of logs that they turn powers into multiplication. So instead of to the power of gx, you can get multiplied by g of x. And then you can try and solve this for x. It's still possibly a very difficult equation, but it's certainly not as messy as this. A logarithmic equation, it would be something like log base b, possibly a sum of logs equal to log base b of g of x, possibly a sum of logs. And what you want to do is get rid of the log base b, so you apply b to the power on both sides, and you'll get f of x equal to g of x. So as much as you can get rid of a to the power with log base a, you can get rid of log base b with b to the power. Okay, so I think we're going to do some examples of this and some applications, computer science applications, in the next lecture.